Where's Dan? And I was going to make fun of him. All right. We probably, I don't know, maybe you don't need an example like this, but let's pretend we do. All right, we got a big train, aerodynamic train, Japanese train, with a car, and another car, and Danon on roller skates, getting towed to Grandma's to play bingo. Yeah. Mu is 0.15 everywhere. That is all the wheels to the ground. This thing is accelerating at 2.5 meters a second squared. I think we can assume that way. No turbines to worry about, Reese? What is tension at x1 and x2? Worried yet? Looks kind of intimidating, don't you agree? Well, it's a train. Actually, yeah, I should have the acceleration a lot higher than that. So, we got lots of stuff going on, right? Free body diagram. Well, here's the guy. Block. He's got weight, right? And is there a normal force for the guy in the roller skates? Sure there is. We're assuming all these tensions are perfectly horizontally. So here, if I knew the mass of this guy, I would know that Fn is equal to Fg. Is there any other forces on the guy? You bet. It always opposes the motion. And I have this tension x1 here. And then I also have this car, which has weight and a normal force, and this tension. But what do I know about these two tensions? Yeah, one of Newton's laws, maybe the third one. And we did this in Physics 11. I had a little meter, and two people pulled it. And I said, okay, now, person on the right, pull it with 10 newtons. Right? What does it show? It showed 10 newtons. Okay, now you stand still. Person on the left, you pull it. 10 newtons. What does the meter show? Yeah, it doesn't matter it's the same force, right? This tension is equal to that tension. So maybe that's a little more helpful. There's also something else. Tension on this guy going that way. And there's also friction, right? So then I got this car. This guy also got all these forces, okay? And then I got the engine, and it's got applied force from the motor, and it's got a force back and a force friction. But why would I do all that? That's kind of a lot to kind of keep track of, right? Well, let's start with x1. What's the tension here? Does this rope really care about how many cars is pulling it? Does it care about how many wheels are on the ground? Does it really care that it's a nice aerodynamic Japanese train? Magnetically levitated with no wheels? Okay, no, we don't care. But why? Actually, yeah. There. A lot less friction, a lot less heat involved.
The thing over top too.
What?
They have like a track over top too. So
They go upside down?
yeah. No, they have the track.
I don't know. They might. Again, I'm not a turbine expert. I don't pretend to be a Japanese train expert. Okay. The tension at X1 doesn't care what is doing the pulling or what is being pulled. Well, it does, but I can simplify it. If it's, for this example, maybe it does. But that'll make more sense when we do X2, okay? This one? No. So hope you all made it nice and neat, but you're welcome. Here's the man. Here's X1. There's nothing more enjoyable to hear teenagers complain. Okay, it's on a surface. We got weight and our normal force, which is equal to Fg because there's no other vertical forces on this thing. And we're assuming he's not going up or down. Okay, he's just going horizontally. And we do have force of friction. Okay, so that's all we care about. Tension at X1, right here, if you want to call that Fa, I would say go with it. If that's what you're familiar with, what's the difference, right? That's the applied force. It's a tension force in this case. But if you want to call that Fa, great. What formulas do I need? Force of friction is mu Fn. Okay? I kind of maybe need this guy's mass, don't I? So this guy is 100 kilograms. This is going to be 200 kilograms. Well, look, the guy's bigger than the train, okay? It's carbon fiber, all right? That is going to be, I'm just trying to make my numbers match to what I got here, 700 kilograms. And that's going to be 5,000 kilograms. Is that better? 5,000 kilogram Japanese bullet train? Okay. All right, so do I have mu? Yes, I do. 0.15 times the normal force, but the normal force is equal to Fg, which is 100 mg, 100 times 9.8, 980, 980, so that is 0.15 times 980. Okay, what else do I know? I know this thing called Newton's second law, which says the net or unbalanced force is equal to the mass times the acceleration. So what is the net or the unbalanced force? It's that minus that. And I still get in this question in Physics 12. Well, what's the formula? That's the formula, okay? There is no special formula. It's a concept. The concept is the net force, X1 minus force of friction, is equal to mass times acceleration, okay? It's a concept. It's not a formula. Different for every little problem you might do. Okay, here's the only two formulas I got, that and that. So I'm trying to find X1. Do I know the force of friction? Sure. But let's be a big kid. I'm going to solve this for x1. It's ma plus force friction, right? So m, I know. Acceleration, oh, I know that. And force of friction, I did it over here. That's mu Fn. So what is the tension? What is the applied force as far as the roller skater is concerned? $397? What? Yeah, it's a tension, it's a force. Okay. And then in university level, we'll just say, well, what force does it need to be to rip the guy's arms from his sockets? Something cooler. Okay? Not this year. All right, that's x1. How about x2? Do I really care that this is a 5,000 kilogram Japanese train with no wheels? No, I don't. All I care about is what's going on behind it, okay? But as far as we're concerned, it's this thing sitting on top of that, and it's the guy sitting on top of that. Just combine them into one mass, because the rope doesn't know any different. Okay, does that make sense? The friction's the same for every car. It's all kilograms. Let's just treat it like for x2, I have this. Okay, one block. What was the mass? 700 and 200 and 100. That's 1,000 kilograms. I got force of friction. I got Fg is mg. And I have a normal force. Which is equal to this. Oh, forget it. 9.8 times 1,000. Okay, so again, what's the concept? The unbalanced force is the net force that equals ma. I know x2 minus force of friction is ma. So add ff to both sides. Okay, m times a plus, what's the force of friction? Mu Fn 0.15 times 98,000. 2, yeah, thanks. 9,800. Which will give me $39.70 is the tension or the forward applied force on x2. Okay? So just simplify it down. You don't need all that junk if you don't need